Hello, Calculus. All I'm looking at tonight is the topics for the Math League, and you'll be looking at this at today's work. So the Math League will be given on Thursday since we don't have time with half day on Friday. So Math League test will, first of all, this week we'll cover applications of differentiation. So what possibilities could they do? So one of the applications of the derivative, you'll recall, were related rates problems. So at one time you could eat these up, but I'm not so sure if you still can. So review related rates problems. There's basically four basic ones, and the one is the lamppost one. And if a guy is so tall and he's walking toward a lamppost that's so tall, what is the change in his shadow? So the length of the shadow would be, the change in shadow is right there. So it'll ask something like, if the velocity is, he's walking at a certain velocity either toward or away from the lamppost, at what rate is the shadow changing at time equals 5 seconds? Something like that. So there's the lamppost problem. And then the other pretty basic one was something that's changing, like say a cone or a sphere. So you have a sphere and it's inflating at a given, so the volume is increasing, I don't know, 13 centimeters per second. I don't know. And then they want to know at what rate is the radius changing when time is 50 seconds, something like that. So basic inflating sphere problem. And that could also be a cone where water is dripping out of the cone. And what's another geometric one like that? The cone, the sphere, I don't know. But another type in related rates was, what's the other classic besides spheres and cones, lamppost? Oh, the ladder problem. So remember, you have the ladder against the wall, and it'll say the ladder is slipping down the wall at a given velocity per so many feet or inches per second, and how fast is the bottom of the ladder going away from the wall at, I don't know, 5 seconds, something like that. So those are pretty classic. The lamppost, the cone and the sphere problems, and the ladder problems. So we did a bunch of them, and make sure you look over these kind. And those are related rates. And if you pick out one that you want us to work together on, maybe as our warm-up tomorrow, go ahead and pick one out and we'll do it. So otherwise, you're on your own to look them up in your book or your comp books and review that information. Another thing that we used derivatives for was graphing functions. So if you would review, when a graph is increasing or decreasing, what's the derivative doing? When it's concave upward or concave downward, what's the derivatives doing? What is the derivative doing when it's at a maximum spot or a minimum spot? So just look at how we used I guess we called it curve sketching. So know what each of parts, what the derivatives are doing, first and second derivatives are doing to help with curve sketching, understanding curves. And you'll be asked to actually look at the graphs of either f prime, or f double prime, first derivative or second derivative, answer questions. So you might look over some of our work that was in that area. And the only other application of derivatives was somewhat alluded to here, and that was optimization. So sometimes they'll give you a function, I don't know, it could be a curve that represents profit or wherever, and they want the maximum, the place where this, at what time was this at a maximum, or at how much money was this a maximum. So you're looking for optimization, and that is where the first derivative is 0, because that's going to be a max or a min. But then you can check the second derivative to see if it's either a max or a min, because a negative second derivative is going to be a max, and a positive second derivative is going to be a min. So you can check it that way, or you can look to the left and right and see which way the curve is bending, or which way the curve is sloping. So optimization. Also remember, when you're doing an optimization problem, you'll have some function which you'll take the derivative, set equal to 0, and make sure it's a max or a min, whatever you're trying to get, but also check the endpoints. When I say check the endpoints, you might have a function that looks like this, and your area of interest is between A and B. So in here, you can see the curve will have a maximum right here, and the first derivative is 0. But sometimes the curve looks more like this. So you have a value that's up, and then like that. So at this point, if you're going from A to B, you're going to find a derivative here that's actually a local min, and a derivative here is a local max. But at point A, the value of the graph is higher than that local min. So we end up checking not only for values where the first derivative is 0, but also where the endpoints occur. And so we're going to look at f of c when c causes the function to be 0, and we're going to look at f of a, and we're going to look at f of b, and to see which one is the highest or lowest, because sometimes we're looking for a minimum value. All right, so that's what they're going to look at for applications of derivatives, those kind of topics. But when it comes to applications of integrals, luckily, when it comes to applications of integrals, the only thing they really talk about is area under a curve. So I'll let you investigate that. And we've done that, or we're doing that actually, so we shouldn't have any trouble with that one. Finding the area under a curve is an integral. All right, so that is Math League for this Thursday, and I hope you find this helpful, and I hope you take the time. I will suspend work on Wednesday night so that you can study for it, so I hope you do. All right. I'll talk to you tomorrow.